Spelled correctly.
God.
that would really mess it up.
Oh my God.
I would say I will be rejecting, so it's more clear, because like sometimes like you.
Oh,我知道那个没开始。
Yeah, my group's pretty good.
My roommates, we can always.
What the hell?
你跟中国人讲 AISX 就是什么电影台，中国人才。去抄。我先抄。你看那个 SCN， 它是这个符号。
Hey, grammar check. Crazy.
Oh, I knew it. I knew it. I was like, attendance is gonna be low today. It's all good. Today's an awesome day, actually. I love this day because throughout the whole semester you've been learning everything anew. And what we do today is we'll take a look at that with a new perspective and see how like everything ties together. And if you roll in an email right now, EC points for the folks who came. So get your mobile device. Hey, my ID is such and such. And then like everyone's like emailing like their group mates first. Hey, group mates, no. Just kidding. Give you guys that idea. All right. Get set up.
You read the paper? That's good. So I'm writing the paper report based on how I was not able to get it. Bro, I wrote whatever I want to take for it. Sorry, yeah, it's not too bad. That part of that homework.
Oh?
What is it?
Wake up.
I don't know. I forgot what he
Huh. That's strange.
He's been saying that.
Huh.
I forgot what time this class was. It's just like a random ass class. Everyone looked at it.
It might be my computer. Shoot, I gotta force quit. Completely frozen. Task manager, there we go. All right.
Stop.
Fingers crossed. Oh, yeah, there we go. But my PowerPoint. PowerPoint. Okay. You'd think things just worked. This should work, right? Ah, there we go. Awesome. All right. So, so we're gonna go on the journey. The journey from the beginning of the class to now with a deep perspective of how the landscape has evolved and where it might go next. And then I'll set up, it'll ramp up, right? It'll get really interesting on the second half. And then I'll set up the next paper and the context of the next paper, which is a really, really, I believe, important work. It doesn't get as much celebration as, you know, like your Berts of the world, but I think it's a doozy, and we'll talk about why toward the end. But just some quick logistical stuff. So we're at week 10. We've got a couple, you know, we're coming up to the end, right? This is, I call this the third phase of the course. We're gonna read 4 more papers. We're gonna have final presentations and demos at week 14, and then we're gonna do some fun stuff. Like I'll have my PhD student come in and talk about some of his research, and you'll see it's incredibly aligned with the work we've been looking at. And we'll do some really cool lectures and so forth at the end. So 4 more papers coming up. Polyencoders is next. And I really think that this paper is going to be a big deal later, even though it's old now because a year and then the paper's old. So we're doing more project jams, right? I wanna have some time one-on-one with each group to see how you guys are thinking coming up to the final presentation and, you know, how we can support you guys. We're here to support. Another person signed up for some special support. Thank you so much. Come let us know. We're here for you. So we'll do some group presentations just to wrap up the, you know, like any final thoughts or ideas or bounce ideas off me. So go sign up. I think the email, Roland's not here. I think it's coming out maybe during this class. Any questions, thoughts, comments, announcements, anything? Cool. I know the weather is so good. I was shocked. I think that's probably, people are just like, I gotta get the sun, dude. I gotta get the sun. All right, so we started with NLP. This is where the journey began, right? Because that's the realm for which conversational AI, as we know it, has emerged. It's now an incredibly important, potent technology in our markets, but the science that fuels its relevance is actually not new. So we talked about the lingo of NLP, right? So we talked about morphology. That's the aspect of the science and computational linguistics that is concerned with the word, like what forms a word. It's different across languages. It's different across lexicons. There's a lexicography, like what does each word mean? He plays a bass guitar versus that bass was delicious. That's lexicography. We talked about syntax, how the words relate to each other, right? The man bites the dog bites the man is different than the man bites the dog. Ironically, many of the models that we use and look at will not be able to reason about those kinds of distinctions. And other languages, the order doesn't matter. We talked about semantics. How can we infer meaning from sentences? I saw the man on the hill with the telescope, you know, an iPad with the telescope as opposed to with the telescope as a buddy. It's different if you have the telescope or you're alongside the telescope. That's a semantic difference. The iPad is small versus the monitor is small. They have different semantics. One is a good thing, one's a bad thing, but it's the same word. It's good in this context, bad in the other context. That's interesting, right? Like, it turns out that most sentiment analysis techniques up until, I don't know, 20-something, 2008, would use these dictionaries and look for occurrences, right? Like how many, I have a bucket of words I attribute as good words, a bucket of words I attribute as bad words, and I'm going to count how many of such words is in the sentence. Clearly, that's a very basic approach, right? But that's one of the, that was actually a very well used approach in building systems. We talked about discourse, multi-turn dialogues, right? Like how do we reason about co-reference resolution, right? Like the he in this second sentence refers to President Obama in the first sentence. So who is the he? Who is him? So this is the taxonomy of language that's relevant for natural language processing. And then we introduced some of the tenets of old school stuff, right? These systems were built pre, word2vec and pre-deep learning entering into the NLP sphere. These systems were hyper-designed. They were rules-based systems. Many of these problems, tasks on this pipeline are relevant, like named entity recognition. Named entity extraction is relevant for, say, many of your projects. But some of these aren't as relevant, right? It turns out that parts-of-speech tagging would be an example of very few AI NLP production systems today will start with parts of speech for their design and functionality, right? But that used to be the first starting place. You would have different trees, and then you would check for synonyms and dictionaries. Like there's a database of like all the verbs and a database of all the nouns you care about, and then you check against them. And this is the way it was done, right? But then things have evolved. So for conversational AI, this is a canonical conversational AI architecture, right? You separate NLU and NLG, and then you have a dialogue management system, right? At the core, on the client side, you can do ASR, speech recognition, speech to text, usually happens on client sides. In many devices, there's a standard SDK on pretty much every client-side thing, including the browser these days. And then text will come in. You'll have a dialogue management system to figure out, well, what's the state you're in the conversation once you understand things like intent and entities, and then you'll generate a message out. That's essentially what conversational AI platforms that people build on function like today. And there's actually subsets of these kinds of dialogue systems. You can have chit-chat systems, which may work differently. This is a task-oriented system, so this is the stuff that you'll see in production a lot, right? And so, okay, so what happened when we made this transition, and what kind of led up to it? Well, the big surge happened at the entry point of deep learning, right? And so we talked about deep learning. Every year, a larger percentage of this class is familiar, but for those who aren't familiar, we talked about where it came from, right? It's an insight. Someone observed that the way our brains learn and remember things is wildly different than the systems we're building to feign or fake intelligence. A famous painting that showed that just the neural matter itself is interesting from a learning capacity was the experiment where a pigeon was put into a Skinner box and trained to learn and differentiate the difference between Van Gogh and Chagall paintings. So that's cool. You can take the neurons and you can teach it things by brute force. You can teach it new things that it didn't even evolve to be able to do, right? We would think of this as a high order capability, but we got neurons to do it. So the big innovation, and this is old, right, 70s? The big innovation was, well, let's just mimic that. Like we've learned a little bit about how brains work in a lab. Thank you, biologists and cognitive scientists and neuroscientists and all of those fields. So we know how knowledge works in neurons somewhat, a little bit. Well, let's just simulate it, right? Let's just simulate it with a mathematical structure. And that's how we got to the artificial neuron. So this field of AI, primarily in a production context, used to be the blue box and the purple box. That used to be really what's in production for most of the things. 2010 was really a key year that everything shifted to a deep learning approach. So although there's still a lot of interesting things you can do in this sphere, and it's also important to make the distinction as to whether or not your problem needs this, which is something that a lot of folks aren't doing these days, right? Everybody's using deep learning for a solution. Everybody's using a transformer neural network for everything. It's interesting how that kind of happens. But then deep learning started to take over. And deep learning is a subset of machine learning, as we talked about, right? And machine learning is a subset of AI. Indeed, any system, even the rules-based if-else statements, if you're mimicking intelligence, you are artificial intelligence, right? And you'll hear folks like not really have this kind of taxonomy in their mind. So we also covered the architecture of a neural network, the foundational bit. How does these neurons capture knowledge, right? You have an input, you have these hidden layers, and this is where the knowledge lives, is in your hidden layers. And if you have more than one, it's deep. And if you have one, it's an artificial neural network. It's an ANN. And then you have it make predictions on its output nodes, right? And then we learned some very important foundational principles when it comes to reasoning in the landscape. You'll hear folks say, oh, this model has 175 billion parameters. Okay, well, that is the weights, the biases. Those are your parameters, right? And then you have something called hyperparameters. And that would be, how many layers do you have is a hyperparameter. How many epochs do you use to train for this task is a hyperparameter. Which kind of, what's the architecture of the neural network, and what are the choices made in its construction? Those are hyperparameters, right? So this simple neuron has 26 learnable parameters. And with those parameters, the question is, well, what is the pipeline for training those parameters, right? So then we went through machine learning basics, which is there's a training pipeline, and you guys did this, right? You guys have done this now. You train a model first to be smart, and then you deploy it and use it. In today's world, in most of the production environments, these don't change in production. They don't change live. There has been a few experiments where it changed live, and those didn't work out so good. So you won't see a lot of commercial systems. They didn't work out good because you can't control the data, and the model's going to regurgitate anything that it's learned, right? So we now understand how to do this, right? Because we're doing it, which is cool. And once you have that trained model, you can do really interesting things, right? You have an input layer and output layer. You construct the output layer for your task. This is a custom output layer for the task at hand. This one's really simple. It's a classifier. There's 10 classes. You have an input layer that's constructed for the nature of your input, which is a pixel. That's grayscale. And then you hyperparameter out how many layers are we going to have. Very empirical process. Uses a lot of gut, uses a lot of insights from experience. And then you just train it. You just hit it with a bunch of images, data. Something is learned inside of the model, and then it's able to function. It's able to perform, right? And that's kind of where the magic is. And I was thinking on the car ride over, right? I was like, I've actually criticized a lot that one thing these models don't do. Here's one big criticism. We'll talk about this more later when we get to the super juicy stuff. And I got some nuggets in here that are new. But one of the criticisms of GPT-3 is, it's just memorizing stuff, right? The weights is really just a special kind of hard drive that's remembering what it saw. So that's not interesting. That's not intelligence. And so I was thinking, well, that's interesting. The interesting thing about intelligence is we have this ability to reason, right? We can logically reason through things. If you look at a proof, you can understand it deeply and reason through it. That's what models can't do. They can just kind of regurgitate whatever they learned. That's what GPT-3 does. It just predicts the next word because it trained on predicting the next word. And we don't work like that. We can reason, we can think. And then I actually was just daydreaming in the car, and I was like, well, actually, do we? I mean, is our brains just a special kind of hard drive that exhibits patterns? Could logic be a high order pattern? And here would be the nugget that might be indicative that could be interesting. And that is, when you're reading a proof, you reason about it in chunks, right? Isn't that how we do it? Like, let's say there's a 5-page proof. First, they establish one nugget. You understand that nugget, you use that as a baseline axiom in your head. And then you reason through the next nugget. And is reasoning just the exertion of a pattern where you run some checks? I don't know. It may be the case that the neurons in our head isn't doing anything fundamentally more special than these neurons are doing, right? And we're learning live, because a lot of these neurons are trained once, and then they don't learn live, right? So it's controlled training and deployed with an inability to learn, but we can learn live, and then we can exhibit patterns. If ever you've had a little brother or sister that's a baby, you'll see those neurons learning, because the arms, the facial expressions, everything moves randomly. It's surprisingly random. If you've ever seen a newborn, it's crazy random. And then it just gets a little bit more conditioned as they grow. And then it's like, okay, now the baby can move its arm, and it seems to have control. But that's a feedback mechanism from randomness, right? Like, what's actually going on with intelligence? The baby's neurons are randomly initialized. I don't know. Well, food for thought, right? But that's what's happening inside this neuron. We don't actually know where the 5 lives, but it's in the weights, the combination of the weights, and that's the key insight. That's the key interesting thing. And that leads to a lot of explainability problems and so forth. So, on this journey, so we were here. All right, cool. This new capability lets us train models from data. And in the case of this example, the model is learning from pixels, right? Well, how do you get it to do words, right? And so that's where we went next. We discussed how data is presented to the model in the form of activations in the input layer. That means bits in the input layer of different strengths, and then you can use pixels, you can use molecule concentrations, share prices, anything that you can turn into bits can be in that input layer. Okay, that's cool. We could use ASCII. Why not? Just have it parse chunks of ASCII, bits, bytes. But is there like, how should we represent words in a language, right? Like, what's a really good way to represent words? And we talked about a few things I'm not going to talk about in this lecture, but we talked about using n-grams. We talked about the bag of words featureization. And then those kind of lead to this one-hot encoding, right? Whereas this is where we landed. Okay, now the thing about one-hot encoding is it lacks any interesting information about the word. It's just a unique bit position that's 1. It's the one hot bit in your vector for each word in your vocabulary. So you just If you have 4,000 words in your vocabulary, you've got 4,000 dimensional vectors where there's one position in that that's a 1 for that word. All right, that's very simple. But it's nice, right? It's easy to work with when you're building a neural network model, right? And so it looks like this. You got 8 words, you got 8 bits, 1 hot encoding. So that's what we're going to use for the neural network models. And it's nice to use for the neural network models because you can train the output layer to just give you a 1 on the output that you're training it for in a particular case. So it's a very nice representation, and that's what we're going to use for words. That was the beginning of our journey, right? That was like all the background stuff that brought us into like 2010. This paper was a 2012 paper, I believe, but 2010 is when all this stuff was happening, started happening. Language models, all right. How did we get here? So it's an interesting journey, right? Like we're walking the line of society as a research organism itself. Society itself as a research organism. This is progress, right? Like, okay, we started with solution A, and then we get to solution B. Let's keep going on this journey. So, okay, one-hot encodings aren't great because we hypothesize that you may want to be able to embed in those encodings information about the word. Indeed, if you get super theoretical about deep learning and knowledge, it all goes down to information theory. Indeed, a lot of insights around where to go next comes from information theory. How do you get information captured in the representations, these embeddings, these numerical items? And so that's what motivated the creation of a better representation for words to get more high fidelity information in it, right? One-hot encoding isn't as useful. So we started our research paper reading journey with word2vec, right? Very good place to start because it's actually a simple idea. And the interesting thing that I perceive, or I've observed or perceived, I wouldn't go so far as say as I know or anything, is to watch how, and you can see it in the writing of the papers, to watch how the discovery happens organically and without a clear direction, right? When this word2vec paper came about, nobody was envisioning now what they're starting to call, thank you, Kunle, foundational models, right? Which is the idea of a model as a utility. Like your nuclear power plant is a model, and then you're serving this utility to the world. That's such a fascinating concept. But that's like what we're actually realizing. We built that. We're building that right now. And it started really here, right? Okay, when you look at the line, maybe we can connect some of those dots. But we talked about CBOW, we talked about skipgram, right? Continuous bag of words. These are tasks, right? So the authors had an insight that you can get a better representation through capturing similarity using these 2 tasks, continuous bag of words and skipgram. If you can exercise these 2 tasks in a way where it can predict, well, in CBOW, you have a window of words and you're predicting the missing word. And in skipgram, you have a word and you're trying to predict its window of words. If you train this in a semi-supervised way, just let it read text, its hidden layers are going to get a representation for the words such that related words will be close to each other, right? Because the window around cat and the window around dog is more frequently going to be the same than the window around refrigerator and the window around shoelace, right? Let's just embed that into the hidden layer so it makes good predictions, and then that numerical representation should capture this similarity. And we'd have a better representation, more information in that representation. Then we discovered some really nice properties, right? And this is cool for the paper, but I'm going to try to draw the connection as to then why was this such a world trend? Why do we focus, and I a lot, focus on this paper as like a tipping point, a turning point? Because, okay, this is what the paper showed us. Oh, I have a new task now. We could do, if you do Japan is to Tokyo as Vietnam is to add the math, you'll get Hanoi. All right, sweet, right? You know, you can solve interesting problems, you know, because the differences in vectors have a similar trend where you can apply it to other vector representations for words. Okay. But why was this a big deal? Well, they showed that if you had a better representation that captured more information about the word in its representation alone, you can take that representation and solve many problems. Word similarity with just that representation. Machine translation, just leveraging representations for words. Parts of speech and named entity recognition. You can apply word to vec, the embeddings, to solve these problems to some degree of interestingness, right? Sentiment analysis. You can tool just the representation to solve these problems. Co-reference resolutions, clustering, semantic analysis of documents. So, wow, that's the key insight that sparked a revolution. The key insight is if you can capture representations of knowledge, you can, from this self-supervised task, you're not necessarily teaching it. You're not teaching it to solve these problems, right? You're just letting it run on a corpus of words, and just in the fact that you're taking those middle layers, those hidden layers, and then you're utilizing those weights to be the representation in a vector form of the word, the sentence, paragraph, whatever. That process allows you to solve other problems even when that representation is formed by just predicting the middle word, right? All of a sudden, you can just do all this stuff with this self-supervised pre-training task. And this was the entry point of deep learning revolution in NLP. And it was a turning point, not just for research world, but it was also a turning point for industry as well. And it was very interesting to kind of live through this as an academic because I gotta tell you, dude. So there's a guy named Chris Manning. He's at Stanford. He's like one of the, he was really ahead of the curve, right? He was happy. You talk to him, all he could do is talk about, oh, yes, you do a softmax on this, you could do that. That's all he would talk about. And then a bunch of colleagues in NLP were hardcore computational linguistics, old school researchers. They built a whole career using statistical analysis in different ways, non-deep learning techniques to solve all these problems. And in comes the newcomer, natural language processing, that threatened their belief system. And so for at least 4 years, when I would just chat with different NLP, it would be like 80% of people would ridicule it. Oh, this stupid fad, like this is gonna be stupid, you know. 80% ridicule, 20% believers. Then it was like 60-40, then it was like 20-80. And now every NLP researcher I'm aware of is a deep learning researcher, right? It's just so interesting to watch that transition. And that was actually a slower uptake than in the vision sphere. Vision folks took it right away. It's like 1 year, everybody was on board, right? It's very interesting. I have a whole bunch of theses as to why it was such a quicker uptake in the vision sphere than the NLP sphere. But it's fascinating to see how this happens. And the question is, what's the next thing, right? That's going to be interesting. Everybody wants to be the next thing. Okay, so now we have this insight. And so everybody gets busy, right? Everybody's working hard. The next one, this is the one that actually took over. So there was Vert2Vec for a hot minute, 1 year. Then Glove came in. And you guys could check. Maybe it was 1.5 years. Maybe it was less than a year. Around 1 year, Vert2Vec was like, oh my goodness. And then a group at Stanford actually came up with a different methodology to do the same thing, to capture meaning from kind of a self-supervised process, right? Now, we didn't talk about this paper in the class, and it's because there's not enough time. And it's also because, and I sound like a super biased person, it doesn't actually use deep learning. So this is an interesting nugget, because right after Word2Vec, Glove comes out. Glove doesn't use deep learning, which is fine. There's nothing wrong with not using deep learning, but it has a methodology to get to better embeddings. And I'll tell you what that methodology is in a second. So there's Word2Vec embeddings, the numerical representation, then there's Glove embeddings, same dimensionality, 300 dimensionality vectors. And it's just better vectors. It just solved those tasks even better. And this one actually is what fed into, I mean, you could correct me if I'm wrong, many of the papers that are coming out now will start with these embeddings to do the other stuff, right? They'll start with Glove embeddings, and I think it manifested itself in the papers we're reading, to then drive the transformer, right? So it's in that pre-processing step, it's like Glove embeddings, then you add positional vectors, and then blah, and then you run through. Go ahead.
I believe most of the big models that just learn custom embeddings for everything. So like the most modern ones.
Okay. Yeah. And the positional, like, you mean the subword embeddings work?
So like each word piece, each token has a uniquely learned embedding. The model.
Yeah. So this is another area of work we didn't look at in the class. So and it's the fast text folks that really popularize this. There's another paper that used to be in this class, fast text, and they have a really important paper that showed that if you took words and you broke them down into their phonemes, the subwords, you can actually generate better embeddings with that. So perhaps that's the common thing that folks are using, those kinds of subword embeddings. But Glove was hot for a minute, and it was in production systems. This was uptaken more in production right after Word2Vec. So it was kind of like a little disruptor, and it didn't use any deep learning. So Glove, while Word2Vec is a predictive model, learning models involves the predictive ability, right? So Glove is a count-based model. And it uses co-occurrence matrices to represent words. So what does that mean? How does Glove get to their embeddings? So essentially, Glove will use a co-occurrence probability. It kind of rings as it kind of rings like Sibao, right? You're trying to predict the word based on its neighbors. This one's predicting a probability of the neighbor given the word, right? And so there's a different probability for, say, solid has a probability that ice will be near it, near by some distance. And so you have different probabilities, right? And you can have this matrix where fashion is less likely to be near ice in its location than water. So water is 3 to the 10 minus 3 times 10 to the negative 3, so 0.003, whatever. This one is to the negative 5, so it's much less likely. So you can in a self-supervised way, read a window of words and identify, well, let's build this model of what the co-occurrence likeliness is. So you're simply looking, for every word, you're looking at, given some window, let's say the window is 1 or 2, right? Given some window, if this is your corpus, this is your Wikipedia, right? So I'm going to learn from this corpus its co-occurrence matrix. And so in this corpus, if you look at I, twice, I is near like. So then you have 2 for like, right? And then once I is near enjoy, so you have 1 for enjoy. And so you can create this matrix that's just the co-occurrences, which will capture a probability distribution that you'll co-occur next to the particular word. So you can use this as a vector, right? Why not just use that as the vector? Right? Every single word has its row in this line. Anyone can tell me what the problem is with using that as the vector? Correct. Problem is the vector is too large, like the print. So the vector is too big, so there's an easy way to reduce the dimensionality of vectors. I shouldn't say easy. I should say there's two actually well-established ways to reduce the dimensionality. One is singular value decomposition, the other is principal component analysis. Anyway, you could read more about how SVD works, but SVD is a method where you can take your 5,000 dimension vector and shoehorn it into a 300 dimensional space while maximizing the variance to keep the property of the spaces kind of normalized. So all you do is you count how, with some window size of say 2, how many times did every word in your vocabulary have that other word in the vocabulary next to it? You take those as vectors, and then you reduce the dimensionality with singular value decomposition. And those just produced better embeddings. It didn't use a neural network model. And so that was the winner for a while. Is that interesting? Yeah, I think so. Got one guy that thinks so. Sweet. No, it's all good. Then we read this paper, right? Elmo to the scene. Neural networks back in the mix. And basically on this whole journey, every single technology is doing much better than the prior, right? So I didn't focus so much on the results per se individually, but you guys saw on the paper journey, you got like 5% better, whatever, 10% better. Cool. So there's a key insight here. Researchers are like, well, can we do better, right? And so this has flaws, like this is just how many times does this word appear next to me, right? It doesn't take into account the context of the word for its embeddings. It's the same as, I'm playing a bass guitar and I have a new bass on my plate that I'm going to eat. A cooked bass on my plate. It's two different contexts. So that context has knowledge in it. There's something if you can get a representation that factors that in, that'll be better. And we know that order matters too. So those were two of the things we learned about in the beginning in the lexicography, where order matters, right? And the semantics, where the context matters. So that was an insight. Well, how do we do better? Well, someone said, well, dude, we got neural networks. We got neural networks from the 70s that is good for that. Time series information. It'll factor in the context of the word. So let's use that. And that was Elmo. And then Elmo was the beast. There was so much excitement at this time where everybody, even in UMich department, man, it was like, oh, did you see that? Oh, you're still using Glove? No, you gotta use Elmo. Oh, Elmo burnt. And this was like semester after semester. Wild. Things have cooled off though, because now it's just transformers and we'll make it bigger. You know what I mean? Which is a little bit, I don't know, we need another crazy disruption like this. Anyway, the recurrent neuron, the crazy thing about the recurrent X in this picture is the word. And then the input for your hidden value that you're going to train, the input is the data itself and what came from the previous neuron, right? The hidden output of t-1, right? In the sequence of t words, t tokens, right? So there's a sequential dependency because it's paying attention to where am I, what came from before, what am I looking at now? Let me build some knowledge through a sequence. So we like recurrent neurons. Nice animation to show us how that works. We looked at this, right? A key, and we're literally, we've kind of covered all of the super societally relevant stuff that's driving many of the cycles in the world. Like, this is what the data centers are running. So we covered a great swath, which includes neural networks that have this recurrent property, right? Remember, this is the same weight as it's going through your sequence of words, right? So it's got some issues though. It's not very parallel. It's got this vanishing gradient problem. Folks have innovated to try to solve the vanishing gradient problem, which essentially is whatever I learned over here disappears by the time I get here, right? So if it's like Barack Obama went to store, blah, 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 and accidentally punched a baby, that's more crazy than, some weird bad guy, punched a baby, right? And you might want to capture that. You might want to capture that here, that it was Barack Obama. That would be crazy. I'm not saying Barack Obama, no fake news here, dude. I'm not saying Barack Obama punched a baby. I'm just saying that would be a crazier sentence. So that's a problem. That's a vanishing gradient problem in the context of a sequence-to-sequence model, an RNN. So then we looked at basically the triumphant creation to solve that. I call it triumphant because not many folks use gated recurrent units, GRUs. LSTMs is really the de facto technology folks will apply to NLP problems when they really care about this time series sequence-to-sequence knowledge capturing. It's slow to train. They're usually tiny, though. They're usually really small. But because you can't parallelize them as well, it just doesn't use GPUs well. And they have a very interesting way of a mechanism to address and learn to address automatically, which is always magical to me, that the parameters are actually learned as to how much it should forget and how much it should magnify and output. It just adds a configuration of weights and an architecture, a neural architecture, that will let you measure how much to forget, learn how much to forget, given some problem you're automatically training it to solve. It'll learn how much to pay attention to the current input, and then it'll also learn how much to push out on the next token. It learns that. So it's just got the machinery to learn that. Super cool. And all of a sudden, sequences of an order of magnitude longer, these networks got really good at capturing representations for. And it looks like this, right? You have actually multiple hidden layers of these. They're stacked. And they're all sliding over your input when they're learning, right? So we learned about LSTMs. Cool. And so this actually it's a very, very nice technology for many problems. Image captioning, you just take one image, and then you can LSTM generate a sequence. Video activity recognition, text classification. You can look at a sequence of frames and say LeBron's about to dunk the ball. I could just tell by the, you can predict that. And this would be the frames, dunk. Dunk would be the class that comes out. Video captioning, which is as the frames are going, I'm going to be writing. I'll write text while the frames are streaming by. So live announcing. Those are such cool tasks. And then parts-of-speech tagging, language modeling, you could do a many-to-many, right? Look at a whole chunk and make predictions as you go, right? And so NER would be a great example of this. You're streaming through the input and you're predicting, is this the beginning of a token? Is this the beginning of an entity, end of an entity? And you guys are building this stuff, by the way. You're using all this stuff, right? And training it, which is cool. So Elmo said, well, you know what? Let's use that technology, classic technology, and let's build a way to have it self-supervised learn a representation for words. A very reasonable thing to do. And they came up with this approach. And it's really interesting to see how the approaches are being constructed and construed and then evaluated. And for everything that worked, like an Elmo, there's about 10,000 ideas that didn't work. Yes, sometimes it's painful. So yeah, you take some n number of these hidden layers. Let's say that's your vector size, and then you get an Elmo representation in the context of the word for that word. These should be better representations. And yeah, it destroyed, right? It did. No longer was Glove super interesting. as a mechanism. And at this point, we're starting to evolve an understanding of going beyond word, right? Like, it was very word-centric world at the time. There's doc2vec. There's all kinds of techniques people started to tinker with, well, how do you do a chunk of text? The most simple was take all the word embeddings and average them, which a lot of folks were doing that in the beginning. It's not the best. And then, like a year later, in the labs at the university, and we still aren't done with BERT. BERT's still so hyped up. And now after GPT-3, now everybody's about the generative models, right? So maybe BERT's coming to a close here. But okay, so there's problems with the LSTM, right? It's slow to train. It's hard to wield this model. If you want to try many different things, if you want to train it on a lot of text, let's say the internet, it's not a great model to do that. So the innovators, and it's so great to just look at the ingenuity of our species, right? So some very good scientists developed a way of representing context in parallel using the attention mechanism, right? Which we talked about in great detail. And essentially, what it is at every layer, you'll have a set of parameters for how much does all the other words in the window of words I'm looking at, how much should that be weighted to impact what I learn, right? Or what I infer. And so for every word, you can train these parameters. This is automatically learned on the journey of training in a self-supervised way. So these aren't like parameters you tune, you know? And that's always just such a beautiful thing about the nature of backpropagation with SGD, because you're searching for the right numbers to get the answer you want, right? And so, you know, it should really factor in street, animal, some of the other words. Then other words like the doesn't, if it tries to dedicate too much learning capacity to the fact that the is here, it's not gonna be as efficient. So it's also a way for each word to kind of ignore words, right? And it's done in parallel because it cascades up. Massive, massive innovation, right? So these are bigger, beefier. They're much bigger models, even at their most rudimentary. These are inference with a good LSTM production grade. Inference is in the microseconds, right? The training it is the hard part. Training takes much longer, but inference is crazy faster. So I like it for that too, but whatever. But these are beefier, right? Because you have multi-head attention. So it's not even like one attention. This is just one. You'll have 8 different, if you have 8 multi-head attention, you'll have 8 different representations over the same window that you can, more learning capacity, right? So you can think of it as more dimensions, more features one could learn, right? One such multi-head attention could learn, feed forward. This was then the best. It's multi-directional, so you get that bi-encoder effect compared to an Elmo. And you don't have the drawback of the training complexity. And then it's not auto-regressive like GPT, which means GPT's task is just predict the next word, right? And so it has the benefit of, in parallel, doing capturing context well, right? But that wasn't the only thing. And there's multiple papers here represented, right? Because we talked about attention is all you need, which is the doozy. And then this was the machinery, like let's build something with that insight. And then the BERT paper showed, well, how do you take that machinery and operationalize it for NLP? And so the idea of Now let's look at pre-training with a self-supervised task. This is where the masked language model came in. I'm just thinking, I wonder if I'm losing anyone. Am I using a lot of jargon that like, am I using any words that I should define? Feel free to just ask me, right? Ask me if I say something and you're like, wait, what was that? But it's using MLM, masked language modeling, which means in my chunk, let's say I'm looking at 1,000 words at a time, I'm gonna randomly like hide 15% of those words from the model, and then my challenge for the model is predict what those 15 words are, right? Just go do that through, Google Docs, right, or Google Books, right? So you look at that task, and then also predict what the next sentence is, right? If you could randomly choose any sentences in this paragraph, I want you to learn to predict accurately what the next sentence is. So you give this transformer-based neural network that pre-training task, and then the efficacy of the model that comes from just adding to the baseline model, just adding one layer for your task at hand and doing some fine-tuning, you can get incredible performance at your task, right? And so this actually really drove home the methodologies around what now Kunle is trying to coin as foundational models. Just look up Sam Bonova and Kunle. He's a good mentor and friend, and he's crushing it. He's crushing it. So yeah, he's built a chip. They just raised $1 billion or something, and he's built a chip for the future of all AI. And his idea is, I'm building the platform to support centralized nuclear plant neural network models that fuels the world's intelligence. And it's brilliant. He's having a lot of success there. He also invented multicore. Literally, he wrote the paper on going from a single chip processor. They used to call them SMPs. SMP is the single symmetric multiprocessor. I forget. But anyway, he wrote the paper. CMPs is what I was thinking. Chip multiprocessors. He wrote the paper on that, which is crazy. So they call him the father of multicore. Anyway, that dude. So this actually laid the foundation for that insight, right? And also laid the foundation of what we currently enjoy as GPT-3. The business prospect of GPT-3 is what's driving that economic interest in building these nuclear plant models. Any questions on any of this so far? I realize I've just been talking. Any thoughts, comments? Anybody wants to work at Sam Bonova? Yeah. People are like, I want to work at that. Go, what? I want to work there, dude. Yeah, I feel you. I could always do an intro. Yeah, anyway, so this is really cool. I mean, this evolution is really, really fascinating. And you can see why it engenders so much passion in people. Because it's an area that's evolving rapidly, and the changes and the progress is huge, right? Huge implications. Just change the top layer for your task and go. Capture all that good, juicy knowledge in the core, and then just train your top layer. Awesome. So thank you, Bert, for that. And then what happened? Of course, the community goes crazy, and then there was infinity Berts, right? So this is one picture. There's actually a lot of other variants not covered here, but there's Ernie, of course. You gotta love it. Grover, Elmo. I don't know, like, what is up with these people? Like, they just go with the metaphor hard. There's Big Bert. Is that even on here? There's Sequence Bert, Gan Bert, Distill Bert, Roberta. Roberta's good because that one is a very robust set of ideas. But these are all different little tweaks to the idea, right? Let's change the pre-training task. Why are we doing MLM? Let's do something else, right? Let's figure out a way to encode like a knowledge graph in the input layer in our representation and from pre-processing and see if it learns better for some tasks, right? Actually, I think was that Ernie? I forget. But yeah, so there's all these different little ideas, right, on BERT, but it was a big doozy. Now, T5. T5 is a very interesting paper. Because actually, as time passes, hindsight becomes even clearer as to what happened in this history, right? Because this is all going on at the same time, so you don't even know what's going to be big. That's why I'm predicting polyencoders are going to be big later anyway. Plug for polyencoders. T5 was actually a big deal. Because at least in the consciousness of the community, T5, because I used to attribute some of this to BERT, to GPT-3, but now when I look back, a lot of this should be attributed to T5 because the whole BERT perspective of the world is embeddings, right? Let's take that representation, that encoding, and then let's use that to do something. So you can take that representation, add a little layer, and then it learns really fast. Yay, right? It's an encoder view of the static intelligence after you train the model. Oh, go ahead.
Wait, you said that. So when I was looking online, like trying to fine tune models, everyone was using BERT for fine tuning. Is that why? Because it learns quick on small data sets, or?
Yeah. So BERT is really when you want an embedding. BERT will give you embeddings that are useful, right? So the pre-training on BERT is a good mechanism to capture knowledge, and fine-tuning is I want to add a layer of neural network goodness that's specialized for my task, so I can just make the whole model a little bit better. The decoder side of the world is what brought the notion of prompting, and that's what T5 brought to the stage. So yeah, I think it's when it comes to getting an embedding, you get embeddings from the encoder part of the model, but the decoder will just generate text for you. They're used as generative models to write text. So, yeah. But I think it'll make more sense when in 2 slides, the distinction between looking at these two worlds. Good question though, very good question. Anyone else? So this part of the model is good for getting that 300 element vector, right? I want an encoding that captures knowledge. This part of the model is incredibly useful for writing text, right? So I'm going to write a paragraph for you based on some knowledge. In the scope of the whole model, the encoder is capturing the knowledge, and then the decoder is going to generate something for you. So this model is actually really perfect for translation, right? And it's kind of interesting because the model never knows what a noun, verb, or adjective is, and it doesn't have to. It just knows how to capture a representation of 3 paragraphs. This is what these 3 paragraphs really mean in this 1,000 element vector. And then I'm just going to use that. I'll just use that representation to then write some Spanish based on it. And so what T5 did, though, was introduce the mighty prompt, right? Unifying the training objective across tasks. So what they said is, look, instead of adding a layer to fine-tune to get the answer you need, just literally ask the model to tell you, right? I don't have to take this weird representation, internal bits and bytes, and then add a neuron that'll tell me the answer, add a head to tell me the answer. Just ask the model, right? And so this paper claims to be the first to introduce a unified approach to having it solve arbitrary tasks. Let the model tell you. That was in T5. GPT-3 just gets a lot of love because they did it in a big way. They evolved on it. So that was very interesting. But that's a big paradigm shift because the makings of zero-shot everything started here. And the paper even, it's almost like they have it in their blood. When you look at the paper, they have it in their DNA. They don't really say it loudly. They don't say zero shot, zero shot, zero shot all throughout the paper. But you could see they're so close to that insight. And then And they demonstrated that this works really well and even better than just using the encodings itself, right? And then there was GPT-3. There's not much special about GPT-3 in its time because GPT-2 was already like years old and nobody was paying attention because BERT was everything in the community. You know, it's like, okay, OpenAI have their GPT-2, whatever, their BERT, y'all. Everybody was talking about BERT, right? So they were like, oh, man, let me take my GPT-2 and I'm gonna make it big, right? I'll just take the same tech, same model, and for one BERT, this is the size of a GPT-3. But I need another page because it goes on. It's that much bigger. Oh wait, actually, there's another page. Actually, another page, and indeed you need hundreds more pages to represent the size difference between these two models, right? You're going from, because everybody's like, oh, it's 175 billion parameters. It's hard to really know, like, okay, GPT said it was like 110 million, T5 was like 220 million, it was two of them. You know, it's like, oh, well. But when you realize how much bigger it is, that's a lot. And I asked myself, just anecdotally, I was like, were the OpenAI people just like, oh man, we're out of ideas? I don't know, this is probably wrong, but we're out of ideas, everybody's talking about BERT. We got our GPT, we're OpenAI, we need to be the best at everything. Let's just go like make it big. That's probably completely fictitious. Maybe there was a very good, they would probably not say that, so. But the optic to me is like, But this started the whole revolution. It's $4.5 million to train. And they were like, okay, now we have this ridiculously large thing. I don't even know how they landed at 175. Was that in the paper? Did they say why 175 and not 200 billion? Probably not, because everybody's doing bigger now. Everything's just going bigger. Okay, cool, do it. And they just said, all right, take this model. This is all simplification, right? Like they actually cleaned the data and they shaped it. They mixed in some, it was like literally like alchemy. They were like, okay, let's take the internet, let's clean it in this way. Let's mix in some news here. Let's mix in some other stuff. We want to balance this internet data. So it was actually very, very architected. But essentially, this was the principle that they were trying to do. Let's just run it on the internet and see what it does. Now, the crazy thing is, and then, before I say, and then, they really honed in on this taxonomy, right? The zero-shot, few-shot mindset. And this popularized it in the consciousness. It was not the first paper that mentioned it, right? So it's almost like it's like I'm chipping away. I really don't have an axe to the guy with OpenAI at all. I'm just looking at research and editorializing it a little bit. But like, so they named it. They showed how it could work. They really took the prompt engineering. They wrote it so well, too. It was so well communicated in this paper. In the T5 paper, it's kind of almost like you have to be a scientist to understand really that they're saying, really, like this, it's like, oh, prompts, yeah, that makes sense. They show examples. They can show how things work. And so they showed that you could just start the model off and ask it to tell you the answer, right? And it solved many problems, and it did things that no one thought it could do, right? I mean, maybe they did, but their paper didn't have code. This happened after the fact. So I don't know if they built the model knowing it can write code, but with a language description. And folks are still discovering interesting new use cases for just that pre-trained behemoth. And that actually is a proof point that's leading to this new term of foundational models. So, and it seems to make sense, right? Like if you envision what society could look like in the future, why not? I mean, if model capacity could be exercised in such a way that it learns a lot if and only if you throw millions and maybe billions in the future on training it, then why wouldn't we organize society around, we've got our power plant, our water distribution line, We've got our cell towers and cell networks. We've got our AI plant, you know what I mean? You know? And then you pay, every household pays $10 a month, I don't know, for AI. Oh, is your AI on? I'm out of it. My AI is all messed up, you know what I mean? That might be our future. What the heck is happening? I don't know. Anyway, that sounds like a crazy future. Especially considering I lived at the time when there were no cell phones at all, like car phones. That's wild. And then smartphones was like, that's like yesterday that happened. 39, whatever. Anyway, so that was GPT-3. Awesome. And this is now when it comes to the hype in the market, we're in the midst of the large language model hype. I don't know if we're coming up on the tail end. I don't know what's happening. I don't know what's going to happen. But this is interesting. And it's sad for researchers like me because it's not like I can just get like $5 million to train a model every day. You know what I mean? It's like, but of course, Google can just whimsically be like, you know what? We got some extra data centers not being used. Let's exercise them with this model. That's and T5 did this. There's a T0 paper. And you can see the battle, right? So like T0 is now, is definitely trying to one up GPT-3. You should check that paper out. It's a very interesting, next time or next year or next 2 years, I'm gonna be teaching T0 for sure because T0 is, you just Google T0 paper and take a look. It's very new, it's like 2022. Right, and it does magical things, which is nice. And this is a preamble. Now, this is actually a little bit of my research perspective coming in here. And this is leading up. So there's zero shot, 2 styles, question mark. And anyone who's super well versed in the literature, let me know if you're observing some new papers coming out, because there's papers every week coming out. If you've seen something that's making this case in an elegant way. Actually, FLAIR, the model that a lot of you guys are using, I got the idea from the FLAIR work. I got the perspective from the FLAIR work because they have the perspective. So, okay, so there's the zero shot, write me an answer, right? BERT doesn't really deal with zero shot. They're a fine-tuning creation. Fine-tune, add a model, train it a little bit, get your answers. But you can also write me the answer, but you can also score me the answer, right? By encoder. It's popularized in ranking systems, and search, and all these other use cases, QA systems. Actually, the QA that you guys built in the warm-up is built with bioencoder. There's bioencoders everywhere. So you can actually take the embeddings and formulate it with a zero-shot formulation too. And the FLAIR paper, there is a FLAIR paper. One of the FLAIR papers talks about this in detail. It's a problem though. We could talk about it. We could read about it. When you read the polyencoder paper, we're going to talk about it Monday. Because in the polyencoder paper, it's going to show you bioencoders. It's also going to show you something called a cross encoder. And then it's going to show you their polyencoder, which I actually don't know how much how durable that architecture is, because we've played with it and we can't get it to work as nicely as the paper says it should work. But and there's some magical hand waving in the paper, whatever. But this bioencoder, you can actually formulate your tasks in such a way that you can just take the scores of 2 text inputs and turn it into a classifier. And if you can turn it into a classifier, you can also turn it into entity extractor. Essentially, all models are fundamentally some type of classifier. And so you can formulate bioencoders. These are 2 BERTs, by the way. And we'll talk about this in detail. But you can there is a formulation of your encoder piece so that you can do zero-shot goodness. And I think this is nicer for what I kind of phrase as live shot learning, where the model's in production and it can learn a little bit as it lives, right? There's some problems with that because these models are big and you don't want to, every user shouldn't have 2 BERTs to themselves. You can't scale that. So there's a way maybe you can just train a few weights as you in production, right? So anyway, I think that this is interesting. There's a Flare paper about it. We could link it to anyone who wants to read a little bit more to get the context of how that fits into the storyline. The sad thing about Flare is they did like phenomenal work. They're really good at pushing things open source. They're awesome. But their paper is not at ACL, NACL, EMNLP. You know, like there's the top tier, and they're at like Coling, which is like 1.5 second tier relative to ACL. So it doesn't get talked about that much. But the open source community like loves it because it's very well done and it's got a lot of documentation, you know what I mean? And it's like, so they're in like Frankfurt or something, so someone probably knows. That group, it's a research lab. Anyway, so I think this is really interesting. But this is actually what the world is obsessed with. And these have to be huge. The other thing is, if you can train these a little bit, you can get zero-shot formulations that you can actually fit on your computer. So I think that's really interesting. Oh yeah, and I didn't talk about Electra because the last work we did was Electra. GPT-3, just the evolution was cleaner because Electra is kind of like on the side. It's like one of the many BERTs, right? So Electra. So this is another work we looked at in the class. And it's in the realm of many BERTs, right? It's, well, how could we get BERT to be smarter? We want higher quality representations for chunks of text. And so in addition to all of the other ways you can try to improve it, this was an interesting way because it used the generative adversarial network, where you can envision you have a neural network challenging another neural network and they're learning together. One's learning really well to battery low. I probably could make it to the end. I could probably make it to the end. Yeah, let me plug it in, whatever. So we talked about this in great detail in the Electra class, but you essentially have your generator that's trying to trick a discriminator, and the discriminator needs to decide if they're looking at a real picture or a fake picture. And so they'll perturb, they'll have like small perturbations in the picture that makes it fake. And so the discriminator has to learn really well how to detect those perturbations. And then there is learning that happens in the discriminator and the generator. The discriminator is like your detective to detect fakes, and your generator is your forger that's going to try to fake the images for you. And then I showed how good it is in the vision sphere. It's like, what? Oh yeah, these people aren't real. If anyone missed that class. These people aren't real. Like, what? Did anyone go to the website after and tinker with it? Isn't that crazy? It's so crazy. It's like, what? It's nuts. What else can you do with it? Well, people are doing a lot of really interesting things in the vision sphere now, right? Like they're animating like Mona Lisas and stuff. You know, there's like tech where you can make Obama say anything, you know, like, yeah, you know, I did actually punch that kid in the face. Whatever, right? Like, you know. So it's crazy what's going on. And they're having fun. I don't see the products, but they're having a lot of fun. That's crazy. So what happens when you apply this to language, right? Like this paper really looks into that idea, and you can see their struggle. One thing in the paper is you can see the struggle of folks, and it all comes at the end, right? Like they're like, oh yeah, and we did actually try a more natural one where we trained the generator, we tried this, we tried that, we tried this. None of it worked. So we're just giving you this kind of somewhat like not very satisfying story where the generator is fixed and they manually make it small so it's a little bit stupid, but they don't want it to be super bad because it needs to give plausible replacements. And then the discriminator just learns from that, from some fixed design point for the generator in this adversarial way. And this is the same picture, but just drawn in the style of this diagram. I mean, it works really well, right? You learn faster is really what they kind of conclude. Although I think with a little bit more time, they would have been able to show some bigger results. And that was Electra. So that was the whole class so far. Does anyone have is it interesting to see it synthesized again? Like you get like, oh, those nuggets that didn't make sense the first time is now fits into a context? Yeah. Is there any questions or thoughts or comments or predictions of the future?
Is Electra like, so is so you said GPT-3 is like, is that a bigger BERT, you said?
Oh, it's a transformer model, and it's way more parameters. Yeah, so it's bigger, more layers.
Electra is like after, or?
Oh no, it's not. It's not sequential. Yeah, I actually plucked this one out. I plucked this one out because in the sequence, Electra happens around this time, right? Electra is one of these. They should have called it Electra BERT. You know what I mean? Because Electra is using BERT. And then the final model is the same size of BERT. So it's another BERT, essentially, methodology. So really, Electra comes in right here between these two. But the storyline of going from word to vec, then better word to vec with Elmo, and then we had BERT, which was the doozy, then T5 with the insight around prompting, and then GPT-3 that just takes that insight and goes nuts. And that's what everyone's talking about today. Although there's so many contenders trying to get some space. People still talk about GPT-3, but you guys know, there's like many different ones. Everybody's trying to fight, all the big companies. But that's where Electra sits in the timeline. But I put it at the end because it's interesting. I include this because it's very interesting, right? Like, this doesn't happen much in NLP space. This generative adversarial network is not something that a lot of people are researching. And I don't know why. I think it's because it's hard. I think it's because it doesn't work. Truth be told, I actually played with it too. And it's very hard to make this thing do things you would expect. But so much in AI research, you're going to have an idea that's just a no-brainer. You think. It's like, clearly, this is going to work. And then you'll implement it, and it just falls apart. And sometimes you won't even know why, right? Like, why can't you use like a T5 GPT to write text, and then you randomly give a BERT real text, fake text, and have it tell you which one's real and fake? It's crazy. It's crazy. But this is a very interesting idea track, and I'd love to see more papers, more research into how we can bring GANs in to make language models smarter. Maybe it has to be like a GPT-3 versus a GPT-3 GANning each other. Nobody's doing that. I don't hear anybody. People are still just making the models bigger, cleaning the data more. I don't know. They're not really fundamentally trying new crazy things, yeah.
Yeah, so like when we've been like researching stuff and like on Hugging Face, like all the models that people mostly use are like BERT based, like for like entity extraction, like intent classification, question answer summary. And then the one thing that I did see like GPT was used for is like text generation, but like it seems like still BERT is like the main thing that you use for everything else.
Yeah, and that's exactly right. And the reason that is really text generation started to become super interesting with GPT-3 because they were able to get it to beat BERT by making it really big and train on the internet, right? So then text generation models are super interesting, but there's a reason why OpenAI is an API, right? Hosting, if it's that much bigger, could you imagine what an inference looks like? How many machines you need to do one inference? Or could you imagine how, it's just, you won't be able to download this model. There's no, and run it on your computer, right? And so it's prohibitive. This is kind of the thing. This is why I always kind of, you could tell I'm like large language models eye roll, kind of like the NLP professor I was talking about. I'm just like, oh, large language, I don't care. It's because it's unwieldy. Like you can't tinker with it unless it's behind some API today. Now that's starting to change, and there's some folks doing some work to try to change that. For instance, Facebook, they released OPT, I believe it's called. And OPT is supposed to be, I want to play with it, I just don't have time. OPT is supposed to be as big as GPT-3, but you can run it on like 12 computers or something. with 12G, and you could train it in some fixed time in 12 days. Let me see if I can find something on it. Facebook OPT model. Yeah, here we go. All right. I suck at doing the screen. I gotta look here, and then I gotta do this. Boop. And this guy. So they have this OPT 175B. So 175 billion parameters, and they open sourced it. So you should, in principle, be able to train this thing as smart as GPT-3. And they say something about 12 GPUs. We believe the entire AI community, academic researchers, civil society, policymakers, and industry must work together to develop clear guidelines around responsible AI, et cetera, et cetera, et cetera, et cetera. Get as big a PR win as possible, et cetera, et cetera. But this is how people have been frustrated that big companies, this trend towards these big models is going to be controlled by these organizations. And so there's a lot of folks that care about making this stuff accessible to everyone. And so there is this model out there. I think it's interesting to try to see what you need to like train it and build it. But there's information, access to open source model, scale. Our world is changing though, man. Like, and I love it. Like everything's becoming open, everything. I mean, maybe it'll probably won't happen, but could you imagine if Twitter was open? That would be sweet, right? You see the whole code base of Twitter, why not? I want to see it. You know what I mean? Like, so it's, I don't know. He promised to open source it. Let's see what happens. Do you think he's gonna do it? No. He's not gonna do it. Reality hits you in the face when you step in and you're like, oh my God, like there's so much at stake. Anyway, but yeah, so feel free to. It's only 1/7 the carbon footprint as GPT-3. I don't really know how this works because it's 175 billion parameters. Like, why is it 1/7 the footprint? It sounds like it's the same number of things. Anyway, so you know, I'll probably end up tinkering with this like in the next year. Cool. Any other questions, thoughts? Awesome. Well, we got some more papers coming, right? And I hope you guys are excited about this polyencoder thing. Like, what is this polyencoder? It's not even casting. So we got polyencoders coming up, and then we've got a couple papers. These are choices. These were choices by the groups. It's going to be really fun to read it together. And then trade is really important because this is a meaningful dialogue system. So now we're going to go multi-turn and look at how you build a single model to do all of your dialogue in one bucket, right? Which is different than the whole entity intent philosophy. Cool. Awesome. Well, with that, I guess we'll wrap until Monday. And don't forget to sign up for one of these slots so I can meet with you guys and see how you're doing.
Monday is Sunday.
Awesome. Thank you all.
I think that's just during class.
Yeah, we should try saying a 2:30 spot.
What?
A 2:30 to 3 spot?
Yeah.
It doesn't really matter.
We love it.
This was essentially
When to use that instead of just
how to plug a light center up. Like these light centers have these dips, right? Yeah. So we had to take a look at all these dips and then match them with an element. That's so ass, dude.
That's crazy. What's the reason? Why? It's for my one class. I have to like run something and it takes like 10 hours to run.
So it's like this is like the bottom.
Switching that to
But if you actually find a text generation you see, I was super curious. So all it takes these models that are big, you don't use them all. So I love 1,600 test cases.
Keep close to like responding to people's like complaints in the midterm evaluation. So I'm on the
Yeah. So let's connect. Yeah, let's connect.
You just walk through like
Oh, good. Some people on Piazza just like honestly, like it's because we were like,
Oh god, no, I didn't even read that.
Exactly.
oh, did it really? That's good. Yeah, see, this is. Did I ever tell you guys about like? I think it was like 2 semesters ago, 3 semesters ago, the 3 cent Piazza post.
like PC servers. Okay, I have a couple servers.
Final exam. Yeah. Oh.
For 3 cent. Yeah, I mean I don't like servers like big and like noisy.
I was in that class during that.
Like in Vietnam, so like PC servers.
Not even just like difficulty, like planning out. It was so terrible.
Yeah, you changed the login to comment and somebody
No, it's not just one. Every student was commenting. Well, because here's the thing. Like,
I mean you can use like one of the Dell's
like 7 or 8 test corrections, and like 4 of them were like test correction that just wrote on the board that like completely changed.
when you hover over it.
He's reinforcing the community.
It's not reinforcing, it's an algorithm.
So crazy. But then, like, you know, you walk in, right, and they handed me this like packet, and I was like, wait, what is this, right? Because it was like, it was a 28-page packet, right? And I was like, what the fuck? That was the final exam. It was 28 pages long.
I had a friend who took that class last semester.
And then after came back and he was like pissed off.
Yeah, God.
Like,
Oh no. So then there was like this IA reply to all the Piazza posts, and then she just went on this like teary-eyed like, if this is the worst thing like that's ever happened to you, then you have lived a very privileged life.
was that the professor?
He was an IA.
Oh, that. I don't know, that's just.
Why don't we just meet without my laptop?
Can you just go grab your laptop?
It takes you like half.
It'll take you 15 minutes.
Oh, maybe you can use like the library computers and remote it.
Are we
You know,
like
it-
actually
it
coding?
costs-
Oh,
I'd like
that's
to.
the point. Maybe I already had an account. That's why.
The idea is that we can actually code, if
Yeah.
people trust to work on their own.
I can just code on my own.
No, we can't be trusted, we just established that.
Yes, they can.
Nobody can be trusted.
We trust.
I've done more work on my own for points than KB. KB's probably done more work than me,
Transfer money.
but I've done a lot of work on my own.
Coinbase.
Roughly the same, I would say.
I don't know about that.
Because I just have money to make.
Most of my work's been due to incompetence.
Because I don't. I'm not using
Do what?
Most of my time has been spent due to my incompetence. So if I was more competent, it'd be less time.
Yeah, I mean in terms of like amount of time spent, definitely.
Why's your Discord so small?
Cause it's not. I know.
Why's your Discord so small?
My Discord is so small. Why don't you just transfer back to your bank?
Look at this.
Old person.
I don't know.
What's that?
Yeah, I don't.
When your phone's small.
Does it all process? Yeah.
It's not the same, you're doing, it's not the same size at all.
Oh, and I did the. Oh, yeah, I do this too.
He's an IRC mode.
Wait, that's not Twitter.
It's IRC mode, it's a different Discord mode, it makes it more compatible.
No. What? No, this is just normal mode. I'm like.
You're an old person though.
Oh my god, it's so.
I'm on the default mode.
You can mess
It's
up
so
all.
weird. Like, it feels wrong. Like, I can tell why,
What's
but
wrong
like,
with
it feels
that?
wrong.
Wait, what's wrong with
Dude's not old person though.
This is why text is stupid.
It's not.
Well, now they're biased because I saw yours
Wait.
first.
Okay, it is kind of big.
It's the default.
No, hers is
There's
the
like
default.
there's like a ton of space.
If
Like, it's not
everybody
big.
else has this,
Are you on iOS?
you're not the default.
You on iOS?
The thing is, it's like a different.
Let's go to Azure.
No.
Why?
You guys installed the coin?
You wanna go get your laptop though? Just go get your laptop for
But
the
don't
please.
lose money on this.
What is that? Sure.
There's like this.
Just go get it.
Like,
Yeah,
trading.
I'm streaming to you.
Screaming at you.
I mean, if you want.
No, I was whispering. I was like.
I'll see one of the work session about doing work.
Do you want?
But I go and I don't come back, and I'll just do it on my.
Why?
just gonna say.
Alright.
Why? Yeah, the whole point is in the library.
I mean,
Oh no.
why are you supposed to I guess
Share programs.
There is no public.
There is a $13.90.
It's an empty building. 15 out of 165.
Very clean, because I use Encoders Pro.
Isn't that in the dude though?
What?
Just right here, like.
If you book those two bus stops, this one has less trading fees.
You guys.
Are you gonna go home? Are you gonna like Discord call?
They're moving all.
No, are you coming back?
Wait, so why do they
Are
have
you
two
grabbing
different?
it?
Well, it's for like, so they're moving all the Coinbase Pro stuff to like.
Are you
Yeah.
Discord calling?
But what was the point of
You would
having
Discord call with us in the
No,
library.
no, it's fine, just like,
like
Yeah, that's
why-
fair program.
just
like
Well, Coinbase Pro is like for a higher volume. Like Coinbase is like easy to get. It's like 2,000.
That's awesome. Yeah.
I don't think I can see my all-time games on sucking, but they're probably hella losses. Actually, no, they're not. They're not hella losses, because I cashed out when what's it called? The Ethereum went up like after it dropped to 2,000, it went back up to like, or after it dropped to 1,000, it went back up to like 1,800. And I bought when I was at 1,000. So, but like, it probably cancels out all my other losses. To be honest. What are you gonna do for the next hour?